So, we will talk about the second module, lecture 2, where again we will discuss the fluid structure interaction, and in this lecture we will give you some summary what would be the influence of, let us say, the cylinder, horizontal or vertical, placed in a fluid medium, and what would be the interest for us in dynamics point of view. We will give a summary on FSI related to this in this lecture. So, lecture 2 will again focus on fluid structure interaction as a continued lecture of the last one in the second module. So, already we said that the horizontal cylinders in uniform flow, when you place an horizontal cylinder, because the orientation of the cylinder, the length of the cylinder, the boundary condition and the physical location of the cylinder, whether it is nearer to the mean sea level, nearer to the free surface, will bother or will affect or influence the overall fluid field pattern around the cylinder in its vicinity. When you talk about an horizontal cylinder uniform flow, so this will going to affect significantly the fluid flow. Let us first look at the examples of horizontal cylinders kept in seawater or in let us say marine conditions. You can have subsea pipelines, you can also have members of floating breakwaters, pontoons, etc., which are all horizontal members. For example, TLP has vertical columns as well as horizontal members. So, horizontal members are called as pontoons. So, these members are generally influenced by the presence of wave and current, and under uniform flow field, the horizontal cylinder will generate waves near the upper boundary only, near the free surface generate waves. As it goes deeper and deeper, the effect will not be there if the cylinder is horizontally placed. So, wave resistance interestingly depends on the Froude number of this, which is given by a simple expression u square by 2g y1, where y1 is the depth of immersion measured from the axis of the cylinder to the free surface, and of course g stands for gravitational value, which is 9.81 meter per second square. So, when the depth of immersion measured from the axis of the cylinder to the free surface is phenomenally high compared to the radius of the member or the cylinder, then the maximum wave resistance will occur. It means the cylinder will resist the wave to its maximum, and this resistance will occur to minimum when the Froude's number is less than a number value of 0.375 as seen in the literature. The references of these are all given at the end of the slide, so you will understand that where this has been borrowed from. So, if the Froude number, if the radius is lower compared to that of the depth of immersion measured from the axis of the cylinder with respect to the free surface, and if that value is very large compared to the radius of the member, the resistance offered with the cylinder for the wave action will be the maximum. So, the boundary effects and end effects, if you talk about the length of the cylinder, covering the ends of the cylinder, etc., will induce what we call 3D effect to the fluid flow in the vicinity of the cylinder if the cylinder is of a finite length. The same story happened in case of vertical cylinders also. In horizontal cylinders the story is again same. So, the major difference between the horizontal and vertical cylinder is in the appearance of the lift force. How the lift force is appearing in the whole fluid structure interaction is the difference now between the horizontal and vertical cylinder. When the horizontal cylinder is located near the boundary, the flow will become unsymmetric, that is very important. It will not be symmetric in nature, it will become unsymmetric, and the lift forces essentially will now become a function of cylinder diameter and the distance of the cylinder from the boundary. Okay. So, as the diameter is larger and larger, the lift forces will become higher and higher. In addition, horizontal cylinders will also be subjected to what we call flow induced vibration. A classical example is VAV, which is vortex induced vibration. So, they will be also subjected to flow induced vibration in addition to the inline and transverse vibrations happening because of the wave interaction. If you talk about the horizontal flow cylinders in a shear flow, because we saw in the vertical cylinders in a shear flow, if you keep a vertical cylinder in a shear flow, if this becomes my flow direction, and this is what I call as a wake region, you will see there is going to be a downward flow here, there is going to be an upward flow here near the wake region as far as the cylinder remains vertical in case of a shear flow, because the presence of cylinder in a fluid medium actually shears the flow. So there is an downward and upward, it shears off the flow, that is why it is called a shear flow, it shears off the flow actually because of the presence of the vertical cylinder. Similarly, let us look at the horizontal cylinder in a shear flow. The velocity variation across the phase of structure will now become significantly important when you talk about the horizontal cylinder in the shear flow. Now interestingly, the ratio of turbulence to the velocity variation across the cylinder is higher than that of a vertical cylinder. So the ratio of the turbulence value to the velocity, which will vary across the horizontal cylinder, is now becoming higher and higher in compared to the vertical cylinder. So therefore, if you got an offshore structural member which is an assembly of horizontal and vertical cylinders, then the vibrations induced because of the flow field on the member interference because of the vertical cylinder and horizontal cylinder will have a different domain of vibrations, as well as the effects on horizontal cylinder are going to be different near the free surface compared to that of the depth located from the free surface. So therefore, if you talk about increase in shear parameter, if the shear parameter in a given flow increases, then the Stokhart's number will guide or govern the behavior of the cylinder in a fluid flow. So the Stokhart's number increase will cause an increase in vortex shedding frequency. The vortex shedding frequency for higher Stokhart's number, the vortex shedding frequency will become high for an horizontal cylinder in a shear flow. Whereas in vertical cylinders we already see in a domain where the velocity reduction happens, and sometimes the inline flow vibrations becomes important, whereas sometimes in the transverse vibration becomes important. In certain case of Reynolds number and Stokhart's number, you will see that the inline flow, that is a drag vibration, will occur at twice of the frequency of the transverse vibration. Okay, the frequency content will be different. So the presence of drag will also be there, plus again a secondary vibration cost, because at the frequency at which double of the transient vibration or the lift force vibration will also occur are present in the vertical cylinder. So when a fixed horizontal cylinder load at a given velocity for a higher positive shear, so the velocity variation because of a positive shear is much more in a shear flow compared to that of uniform flow, which has been also observed in a vertical cylinder. So of course at a free surface the vertical load in both positive and negative shear increases significantly in comparison to uniform flow, that is the difference. Therefore if you got a non-uniform flow, then the variation in the vertical load is higher in comparison to that of the normal flow. So the dynamic vertical loads on the cylinder at the depth or at the middle of the cylinder, because of the positive and negative shear, will have frequencies at an higher level with energy content larger. Okay, the band of the frequency width will be higher. Okay, so at the mid length of the cylinder the energy content will be also higher and it will occur at a higher frequencies. Of course near the surface there is a significant reduction. Any questions here?
is vortex setting frequency?
You want the number or the phenomena? We will explain it. Of course, in the case of horizontal cylinder near the free surface there is a significant suppression of eddy and wake formation. Wake formation does not occur in an horizontal cylinder near the surface, whereas in vertical cylinder it is significant, whereas in horizontal cylinder it is not. There is a suppression of the eddy formation and of course the wake region, and this happens near the free surface. So the location of the horizontal cylinder is very important as far as the vibration phenomena is concerned when you talk about fluid structure interaction for a horizontal cylinder. So there is a steady component of vertical load which increases significantly at the free surface. So at the free surface the steady component keeps on increasing significantly. So at the free surface the steady component of the vertical load increases at the free surface, whereas there is a significant reduction of the wake formation at the free surface. So now we talk about cylinders or members which are in groups. When this is my flow direction, instead of one cylinder I talk about group of cylinders. I can also talk about group of cylinders in a specific arrangement with a phase lag. And of course this is spacing. And of course there is a diameter. So when you talk about the interference of group of cylinders in a flow field, then it amounts to what we call blockage, because the flow field or the velocity of the flow past the cylinder which is in group will get reduced. And we already saw in the last lecture, in case of reduction of velocity there will be different kinds of vibration set in the cylinder itself. Okay. So when the velocity reduces, there is a different kind of vibration for a specific range of 1, 2 and 3, the vibration set on the cylinders will be of a different mode. Sometimes it is in drag or inline effect, sometimes it is in transverse effect. Okay. We have seen that in the last lecture, you can look at the table later. So when we talk about group of cylinders which is encountering the fluid flow, it reduces the velocity significantly and this causes what we call blockage. This is addressed in API very interestingly on two parts. The blockage effect can be on the wave, the blockage effect can be on the wave loading, can be on the current as well. Okay. In case of waves there are no enough evidences. Okay, this is API recommended practice 2A WSD. In case of wave there are very few experiments which verifies this fact, but analytically it is not verified. Therefore, as far as blockage effect and wave loading is concerned, people do not account for the increase in force because of blockage effect on waves, whereas in case of blockage effect in current there has been very good experimental results available in the literature. Therefore, people say that find the modified current velocity because of the blockage and use it in the Morison's equation. Yeah, that is what APA recommends in case of blockage effect for current velocity is concerned. So let us quickly look at what is the blockage factor, how to compute this. So as I just now said, closely spaced members connected in different orientations, can be one on a transverse direction, can be one on the inline direction of the fluid flow. Closely spaced members, when they are connected to each other, okay, remember they are all connected, they are all independent themselves, no, they are all interconnected. When they are connected together, it causes distortion in the fluid flow around it in the vicinity. So the structure is considered as dense in its terminology. The structure becomes dense because of the group of cylinders, therefore the flow field retards or slows down as it passes the cylinder or the structure. So this causes what technically we call as blockage effect, okay, and it complicates the velocity in the vicinity of the structure. So the load on structure increases because of this reduced velocity due to this blockage, and we compute this blockage factor as CBF as given in this expression, where the drag force on each, okay, the drag force on each member is summed up separately and then arrived at for the influence of blockage factor on the structure. So the blockage factor will anyway enhance the load because of the wave action, but there are no experimental evidences thorough enough to verify this fact, therefore this is not accounted in the design at present. On the other hand, you can also look at the blockage factor for a group of vertical cylinders in the other format, which is a function of spacing and the diameter. If the spacing versus diameter ratio is less than 4.0, then you can simply use the blockage factor as 0.25 S by D. If this value is exactly equal to 4, then you can use blockage factor as 1. Of course this is done for each and every cylinder separately and summed up for finding out the drag force on the members. So this is what we already said, S is the spacing of the cylinder and D is the diameter of the cylinder. So in a nutshell, blockage or any group of structures or cylinders kept in a specific orientation, if they are interconnected, they are called as dense structures. The dense structures will retard the fluid flow. The retardation or the velocity reduction will increase the force on the member. Okay, there are experimental evidences which confirms this for wave action, but not been recommended. For current action, yes, it is recommended indirectly by finding out the modified current velocity because of the blockage effect, then use that modified value in your Morrison equation for finding the drag force on the member. Okay. We will talk about now wave structure interaction quickly. So as we saw, whether the cylinders are placed vertical or horizontal, when the wave or the flow action passes through the cylinder, it oscillates or creates oscillation in the inline direction or in the flow direction, which causes oscillating force in the inline direction of the flow. In addition, the free surface also changes, which introduces the additional buoyancy or the submergence effect on the cylinder. If you talk about large structures placed in the wave field, they alter the incident waves itself in the vicinity of the structure. Okay, these are all statements qualitative which have been taken away from different research findings of various papers, which we will refer back at the end of the presentation. So on the other hand, if the dimension of the structure is very large compared to its wavelength, as we all understand, the flow remains attached with the cylinder. That is a very important factor which is being used for finding out the forces on the member using Morrison equation. So the flow remains attached. So that is one of the interesting assumption what we make in case of estimating forces on the members. So this is true one when the dimension of the structure is very large compared to its wavelength. So several procedures are actually used to explain the potential function generated in the vicinity if you know the incident wave potential. For example, flow around the structure is assumed to remain attached. I said it is a large structure, the separation is neglected and the fluid is assumed to be incompressible and irrotational for our potential flow theory. Therefore the structure is also assumed to remain rigid for its action, and of course we do this analysis only for small wave amplitudes. So the fluid flow in the neighborhood is described by velocity potential as given in this expression under the linear theory, where in this case phi is a spatial part of the total velocity potential. There is a spatial variation created in the velocity potential, whereas omega is the frequency of the incident wave, which you already know what is hitting or what is encountering the vessel or the cylinder. The total potential which is present now in the flow field is a sum of the incident wave component what you already know and the potential of the scattered wave component. Both has got to be added together to find out the instantaneous potential at a specific flow field present at that time. The scattered wave component is generally represented by continuous distribution of waves, because it keeps on scattering in all directions as far as the incident wave is concerned when it encounters a cylinder, but it is assumed to be superposition of numerous waves using a specific theory. So it now turns out to be a boundary value problem which is defined in terms of Laplace partial differential equation, which is conveniently transformed to an original partial differential equation in potential flow theory. Now the question here is, where are the boundary conditions? The boundary conditions include the ocean floor, the free surface, the submerged surface of the structure and the radiation condition as the flow approaches infinity. These are the boundary conditions what I apply or what I use for solving my potential flow theory. So if you look at the bottom boundary condition separately, it assumes a flat bottom and it implies the vertical component of the water particle velocity remains 0 at the bottom. The vertical component of the water particle velocity remains 0 at the bottom. If you look at the free surface boundary condition, it equates the vertical component of water particle velocity again into the rate of change of free surface profile respect to time. When you look at the far field flow condition, then it states that the flow at infinity is only an outgoing flow, there is no incoming flow to the system. Okay. The velocity derivative is only in the outgoing direction. So now the body surface boundary condition has two forms which depends solely on the structure whether it is fixed or compliant. We will see both the cases now. When the structure is fixed to the seabed, the normal component as you just now saw of the water particle velocity to the submerged surface of the structure remains 0. So this arrived on a basic assumption that the derivative of the potential with respect to the directionality normal remains 0. When you talk about compliant structures, then in this case the equation is given as it is been shown here, where the phi k is the radiation potential, where n k is the component normal of the potential in k direction, and whereas u n k is the normal velocity component of the fluid particle in all degrees of freedom what you are calculating the forces at. For example, in our case it is going to be 6 degrees of freedom. So the boundary integral technique based on Green function will be used to solve this potential flow theory. This represents both the far field wave potential and near field wave potential both. According to this method, the surface of the structure is divided into small parts. Okay. These elements should represent, however, the original geometry of the structure, there is no change in this. If that is the case, these elements are then termed as lower order elements because of approximation. That is why this theory or this method is called lower order boundary element method. The lower order in sense I am dividing the whole structure into small components whose geometric characteristics remain absolutely similar to the whole structure. okay, that is why this is called as lower order boundary element method. Of course, the problem is solved numerically. There are various numerical techniques being used to solve this potential flow theory problem using BEM, which we are not discussing in this particular course, but anyway there is a directionality of your understanding that what actually the wave structure interaction induces on the structure, and how do you handle the problem, how do you formulate the problem, how do you handle the problem, how do you solve, by what technique. We are just taking you only on that path of understanding this. Okay. If you talk about large floating structures, where again we have an example in dynamics, the linear diffraction problem is solved for a known scattered potential. Now the pressure in the flow field is given by this expression as you see in the slide now, where S is actually the submerged area of the surface in all degrees of freedom. So what you have got to do is you have to find out the pressure distribution at the center of each grid, so called elements what you have divided the whole structure into, and find out the pressure distribution in all degrees of freedom independently at each component. So you are working out the pressure in the fluid flow as given with this equation, where I is for every degree of freedom independently. So once you know that, the radiation condition is imposed instead of the diffraction condition now for your solving the problem. The structure oscillates or considered to be oscillate in simple harmonic motion in the absence of incident waves. The oscillation takes place only in 1 degree of freedom at a time. So that is what your idealization is. The corresponding radiation potential is now calculated using boundary condition, which is appropriated for a given cylinder or a given structure in a C state. So normal structural velocity is now calculated in all degrees of freedom, as you see this expression here, which is include the scattered potential and the radiated potential both R and S as well. So phi r k, what you see here is the forced oscillation of unit amplitude, which is worked out for every degree of freedom, where k is the each degree of freedom separately. Now the radiated potential provides added mass and damping coefficient for my analysis in all 6 degrees of freedom separately. So after obtaining the hydrodynamic loading applied on my member, linearized equation of motion, which is being solved using in different techniques, either in time domain or in frequency domain. That is how I do my dynamic analysis of incorporating FSI in my structural problem, where the cylinder is fixed, or it is large in diameter, or it is floating, where the surface of the cylinder is closer to the free surface or mean sea level. Interestingly, as we also saw, damping plays a very important role as far as hydrodynamic let us say Hausen structures are concerned. So let us talk about the damping estimates very quickly now. Damping is very important when you excite a structure for a limiting frequency, that is very important. Offshore platforms are generally designed not to have the natural frequency well within the domain of the excitation frequency, that is a general design concept what we have in offshore structures. However, in case of flexible structures, more interestingly, the higher modes of vibration will play a role in the finding out the response, which will add more complexity to the dynamic analysis. So we should use what we call modal response method. For flexible structures, or I should say compliance. We will work out an example how to truncate the modes etc. later, but we should use this algorithm if you are talking about compliant structures, because higher modes will now participate in the overall response of the structure. So damping essentially comes from two sources, one is material, other is hydrodynamic. So there are two sources of damping. One is from the material itself, other is from the hydrodynamic side. The material can also come from the surface of the material or the material characteristic as well as from the joints or connections can come from the members, can come from connections. So they will result in a friction model which is expressed by Coulomb's model. So it can come from the material of the member as well as the mechanical connections. So this is basically a friction model which is given by the Coulomb theory, okay. Whereas the hydrodynamic damping will come from the viscous model which we will see in the subsequent slide, but interestingly people have found out from the experimental investigations that the damping which comes from the source of the material is far inferior and lesser compared to the hydrodynamic damping as far as ocean structures are concerned. So generally they are very small, the material damping is very small. Therefore if you look at non-linear dynamic analysis, if you look at non-linear dynamic analysis where the non-linearity essentially comes from the material, this is not a significant application to offshore structures. If the non-linearity comes from the forcing function, for example from the drag, for example from a variable submergence, for example from the system non-linearity, that is because of the stiffness and mass, then this is significant. People do not talk about the non-linearity in terms of material here, they talk about in terms of essentially on the loading component or on the system geometry itself. So talking about flexible systems or compliant structures, you will have system non-linearity. Talking about large diameter structures where we use Morrison equation, talk about drag non-linearities. So the material damping is generally less in compared to that of the hydrodynamic damping, because these are the two sources from which damping can come in ocean structures. So now let us quickly look at the hydrodynamic damping. There are several sources from where this damping can arise. For circular cylinders oscillating in waves which are smaller in amplitude, then the Stokes damping per unit length of the member in a laminar steady state flow can be given by this expression, where the beta value here is nothing but a ratio of two numbers, which is Reynolds number and Quilligan-Carpenter number. Based on this value, depending upon the amplitude of the response of the system, can easily find the Stokes damping per unit length of the member, which can also come from an important source of hydrodynamic damping. Can also find out damping in terms of varying drag coefficient as given by this expression here, which is also available in the literature as an alternative method of computing damping in terms of its drag coefficient. You can use a modified drag coefficient which can account for hydrodynamic damping in a given system, which is given by the following expression, where CD is given by 3 pi square by Kc stands for Quilligan-Carpenter number here. If we look at damping in steady and oscillatory flow, because that was a laminar flow, the previous one was a laminar flow, it is a laminar flow here, it is a laminar flow. When you look at oscillatory or steady state flow, then the damping of the structure arises from 4 different sources. It comes from wave radiation damping, can come from still water viscous damping, can come from wave drift damping and steady flow damping, which all will be function of velocity. Damping can also occurs in the form of linear radiation damping, linear viscous and non-linear viscous damping, which are all function of velocity of the motion of the structural system. So radiation damping actually arises from linear diffraction theory. The load caused by linear damping was proportional to the velocity of the structure, as I said just now. The loads created by non-linear damping are proportional to higher powers of the structure velocity. So they are also a component of or the function of structure velocity, but of an higher power, not a linear one. So the different source of damping which comes on an offshore structure when it is steady and oscillatory flow arise from wave radiation, still water viscous damping, wave drift damping and slow steady flow damping, which are essentially a viscous flow damping models which have been used for our analysis in general, because they are either function or proportional to velocity in a linear terms or in terms of higher powers of the structure velocity. So, in a very brief summary, we have picked up two examples where we have got one horizontal cylinder and one vertical cylinder. We made a flow field past the cylinder. Sometimes we also discuss about group of cylinders and see what is the effect of these cylinders depending upon the orientation, depending upon its finite of length, depending upon the boundary condition whether the ends are closed or open, and depending upon its physical location whether it is closer to the boundary or closer to the seabed. What would be the significant alteration in the flow field and how do you handle this in a classical potential theory as explained in the literature, and how to transform these forces in terms of dynamics importance in fluid structure interaction and wave structure interaction. That is what we have seen in the two lectures. Quickly we will summarize this now what we have seen so far. It is very important for us to understand, it is all these statements are qualitative. Of course I will quantify them later by picking up examples on different kinds of structures. They are very important, it is a very interesting summary given by various researchers which I will show you in the next slide onwards the references. So essentially we can understand that the presence of structure certainly alters the fluid flow field in this vicinity. One important aspect is when the cylinder is vertically placed, it creates a wake region with shears of the flow depending upon the flow field in its vicinity. So it disturbs the vicinity. When the structure is placed in the flowing field, the flow pattern is what people say is altered qualitatively. The restraints are developed in the fluid medium to maintain the position of the structure, that is very important. Okay, the structure does not want to move or wants to move in a specific manner, it develops restraints in the wave field what we are trying to measure, and the response are created because of this kind of restraints developed by the structure on a flow field. So inline forces what we address as drag forces contain both frequencies higher and lower depending upon what is the Reynolds number and what is the corresponding Stokes number. The major difference actually comes in the lift force in its appearance between the horizontal and vertical cylinder. Where does it occur actually? Horizontal cylinders are also subjected to fluid induced vibrations, for example vortex induced vibration VIVs. Importantly, the ratio of turbulence to velocity variation across the horizontal cylinder is higher than that of a vertical cylinder. In horizontal cylinder, increase in shear parameter results in increase in Stokes number, which in turn increases vortex shedding frequency. That is what the answer is. The vortex shedding frequency quantitatively will be enhanced by an increase in Stokes number, which happens essentially in horizontal cylinders, not in vertical cylinders. So orientation of the cylinder will matter whether it will cause VAV or not. So at a free surface we look at the free surface, be it horizontal cylinder, the vertical load in both positive and negative shear increases significantly when you compare it with the uniform flow. The dynamic vertical loads on the cylinder at the middle depth, both because of positive and negative shear, contain higher energy at very high frequencies. The frequencies are very high and the energy content, it means it is broad banded, energy is larger at middle of the section, middle depth of the cylinders. Steady component of vertical load increases significantly for horizontal cylinders at free surface, whereas the variation component dies away. The eddies and wake regions are not present in horizontal cylinders near the free surface. When you have dense structures where there are a series of cylinders which are kept in flow direction parallel and normal to the direction of flow, they cause what we call interference to the fluid flow, which is called blockage factor. Because the fluid flow slows down, the velocity decreases, it retards, it enhances the forces. So loads on structure increases due to this blockage. When the wave passes the cylinder, it causes oscillating inline force on the cylinder, that is very important, that is where we are looking at the vibration point of view. If the dimension of the structure is very large compared to the wavelength, the flow remains attached to the structure. So the assumption of flow getting not separated from the cylinder is very important only for large diameter structures where the diameter is comparatively large with respect to its wavelength of the approaching wave. The radiated potential provides added mass and damping coefficients for my analysis in all 6 degrees of freedom independently. I can find out them. Damping essentially arises from 2 sources, one is material, other is hydrodynamic. Of course, that arises from material is essentially lower in its value compared to hydrodynamic. Therefore, talk about non-linear dynamic analysis, we focus essentially on non-linearity arising from the forcing function or from the system non-linearity, not essentially from the non-linearity arising from the material properties. Of course, it is also present, but we do not look at this in the ocean structures. Predominantly and significantly it will not get reported. Essentially non-linearity plays an important role, majority from the form which is compliant or from the load which is handled appropriately in the analysis, because people always find equivalent linearized drag instead of a non-linear drag. Okay, you can find literature where people use equivalent linearized drag instead of non-linear drag system component in the forcing function. So damping essentially comes from 2 sources, material and hydrodynamic sources. Of course, material essentially talks about the friction model, whereas hydrodynamic essentially talks about the velocity model, which is essentially important for us because our whole analysis depends on C as a function of or proportional to its velocity. So material damping is generally smaller, as just now we said. The load caused by linear damping are proportional to the velocity. It can be linear, can be of a higher order as well. The lift forces contain oscillatory components with multiple frequencies, that is very important because the frequency band are different. As we discussed in the last lecture, there are something called springing and ringing response in compliant structures. Where transient vibration also becomes important. Generally people ignore this, but in this case it will become important. I will show you in one of the case studies we will take up in the next lectures. I will show you how ringing response or springing response can become phenomenally high in compliant structures, because they will be only addressed to the system non-linearity coming from the geometry, not for fixed structures. So people have seen this kind of studies report to the literature, which we will show you and discuss you in the subsequent lectures in this module. So for uniform flow, forces are essentially governed by the Reynolds number and to some extent by Stokes number as well, because we will talk about at what frequency the drag component will appear depending upon the Stokes number. Vortex shedding dominates the type of vibration caused by cylinder in a fluid flow, of course if it is activated, depending upon the reduction in the velocity. If the velocity is reduced in a range of 1, 2 and 3 as we discussed in the last lecture, then the type of vibration imposed on the cylinder varies. The boundary effects and end effects, if it is introduced for a finite length of the cylinder, will cause a 3-dimensional effect on the fluid flow if the cylinder is of a finite length and the boundary conditions are essentially controlled by either closing the ends of the cylinder or placing them to the vicinity of the mean sea or vicinity of the sea surface or the sea bottom. So there are interesting references, these are available in the NPTEL site itself. Just for completion's sake, acknowledging the authors and different researchers, let me run this slide very quickly. So majority of these results are taken from Chakravartis and Naes and Togermoen. Of course you have interesting material available in Dawson in 1983, Offshore Structural Engineering is a very interesting book. If anybody wants to really understand fundamentals of offshore structural engineering in terms of engineering, structural engineering perspective, please read this book. It is very interesting, very simple, it is given in very simple format. whereas if you want to look at the hydrodynamic component of your analysis, then look at the different books. It does not mean Dawson does not address hydrodynamic components, but it addresses the whole issue in structural engineering perspective. It is very interesting, it is available in our library, you can see this book. Of course the construction aspects which we discussed in the last module as well as the present module which you are going to discuss are available in Gervich and Graf. Of course some of the response control of systems which we will discuss in this lectures will be available from Insekik and Hevikoglou. Interesting studies are also referred from Patel and Saidi, and of course we have also a book written on dynamic analysis which also address some of the important components what we are discussing so far. If you have any questions, otherwise we will close. So in this lecture we have quickly seen how the interface between the fluid and the wave, or the fluid and the structure, will impart additional forces in terms of force magnitude, in terms of its frequency content, in terms of its energy presence, in terms of its orientation of the cylinder, length of the cylinder, then how the flow field is altered significantly where the drag forces or the lift forces will occur at a specific frequency which otherwise does not get reported, how vortex shedding frequencies will activate the response of the structure when it is being interfered with the wave or with the fluid flow. If the structures are in groups, then what will happen to the structural system, what effect it causes on the fluid flow as a blockage factor, how it enhances my force coming on the system, and whether the force variation is very high near the surface and as it dies down as it go below the bottom, I mean towards the mean sea level, why does it happen. We have discussed it in very brief, and we have given you an idea that how one can handle qualitatively FSI in the dynamic analysis. How to quantify this is depending upon how do you arrive at f of t on your right hand side of the equation of motion, which we will keep on seeing now onwards in all example problems what I will take in the next modules or in the next lectures in the same module. So qualitatively we have understood how FSI is important, quantitatively how they are carried away in terms of different non-linearities present in the system, how do you solve the equation of motion, and how the system would have been designed so that the frequency of the system is kept off band from the wave frequency, and why the response still are important in specific degrees of freedom only, which we will discuss in different examples. So dynamic analysis of ocean systems will become interesting only when you start understanding and reading different literature parallelly as people address this problem in different domain of interest. All authors, all researchers will not unfortunately or fortunately follow the same style of addressing the problem. Okay, you will find majority papers address the problem in time domain, few of them address in frequency domain, some of them give time history responses, some of them give response amplitude operators, some of them talk about steady state response, some of them speak about transient response, some of them talk about application to fixed jacket structures or fixed platforms, some of them talk isolated only on complaint structures, some of them talk about complaint structures of large diameters. So you have to have an access to different kinds of papers on dynamic analysis of ocean structures to understand really on what domain how people use this as a tool to express ultimately the response behavior of a system in a given flow field. So I am not interested in estimating the forces, remember it is very important. What is the fundamental difference between dynamic analysis of ocean structures and land based structures is that in land based structures stresses and force are important, whereas in offshore structures we are talking about the response. You may wonder why, can you tell me why it is so? Of course moments and forces and stresses are important, but most importantly are my responses. Can you give me a very defending statement why this is important, why this is addressed in dynamic analysis and ocean structures, why not the forces? Sorry? No, no, I mean there is, I want a very befitting reply for this. Why one is worried about the responses? Of course one is bothered about the forces and stresses, otherwise you cannot design the system, I agree, but the focus on responses, whereas the focus is never on responses when you talk about land based structures. For example buildings, bridges, people talk about deflections, but they equally talk about moments and shear forces also. Here I predominantly talk about responses. Why?
and all these.
Okay, functional aspects.
Yeah.
Okay.
So if response will be high, we cannot drill, or the other function cannot be.
Okay, so the functional characteristics or performance characteristics cannot be achieved, the response are undesirable. 1, 2, that is one agreed statement. 2, see, I want to make the system compliant as I want to take it deeper waters, and deeper waters the where I get oil drilling these days. The moment I say the system is remaining compliant, I am not bothered about the forces, I am bothered about the responses. Okay, so dynamic analysis of ocean structures in the present scenario will focus essentially on responses, and of course when you talk about floating structures or let us say compliant systems, stability also plays an important role. It has got to be either neutrally buoyant or positively buoyant systems. Okay, so stability is equally important, but people are more worried about the responses in compliant degrees of it, because the structure need to be floating or flexible, you want to take it to deep waters. So forces may not be that important compared to the responses. Of course if you do not have the forces and stresses, you cannot design it, right. So you need that, but the focus is on responses. That is why generally in dynamic analysis of ocean structures you will see the paper addresses 99% the response algorithms, not forces. Okay, that is the focus why it is being done like this. And there are very interesting examples, I will give you questions. There is a very interesting question, let me see who is able to reply this in a defending manner again. See, I have two comparisons. One, I have a land based structure which is very tall, land based structure founded in soil. This is soil, this is founded in soil, very tall. The moment the structure becomes very tall, height is very large, the structure is flexible, okay, there is no doubt on this. So I am taking an example of flexible system, right. Compare this with a flexible system like for example a TLP, which is again founded to the seabed, of course in a water body, okay, is again flexible. Now I can design the system for wind loading, which is one of the lateral load which is governing the system design because it is tall. I design this for wave loading, which is again a lateral loading, which is one of the governing load for the system for design, agreed. Now the question is, when I impose any settlement because of geotechnical problems, when I impose a seismic excitation since the structure is resting on founded on the soil, the whole force is getting transferred to the members, therefore it can become critical. Now seismic actions can also happen on the seabed, there is no guarantee that they have to happen only on land, can happen on seabed also, right. Now one can wonder that when the seismic action happens on seabed, because of the enormous water depth available here, they may get suppressed and therefore my body will not be affected by the sea or by the excitation. But there are interesting studies where seismic excitation can also cause a serious problems to this superstructure. So my question is not how and why this is causing, my question is, if you want to hypothetically equate these both analysis, here the forces are superimposed on the member because they are connected, but here my superstructure is not connected except to the teethers. How do I actually do, or how do I justify my analysis because of a force which is not happening on the system? See, here the force is happening on the system, I can justify. Here the force not happening on the system at all except that it is connected by a cable or a tether. How do you justify my analysis? Okay, it is a very interesting problem. It is a very interesting problem. How the analysis justify? I am talking about justification only the methodology. You understand the problem. The crux is the the superstructure, so called loading, is not resting on a system where excitation is given. Here is justifiable because resting fine, but here is not. Secondly, there is an enormous damping happening because of increased water depth. Therefore, this signal is supposed to die down as it reaches here. So, should I really consider this? If at all I consider, why and how comes later. First is why and then how. Okay. So, look at this problem and see whether this can be also answered and addressed, or people have done this kind of work for offshore structures. I am not talking about structures which are resting on floor, sea floor, like gravity based structures or jacket structures, because then the problem is equal. I have no difficulty in justifying it because the member or the superstructure rests on the sea floor, you can always apply the seismic action, no problem. Talking about a flexible system which is equivalent to this, which is not resting, but still is it important or not? Justify the analysis. Okay, that is the question asked.